Ice ages can feel like sudden disasters in Earth's story, but they are not random. Over hundreds of thousands of years, the planet moves through slow astronomical rhythms that change where sunlight falls, when it arrives, and how strongly summer can melt the ice. The key is not simply how much sunlight Earth receives in total. The key is summer sunlight in the high northern latitudes. That is where large ice sheets can grow across land, and land responds to temperature much faster than ocean. When winter is dark and cold, snow and ice can build up. That happens every year. The real question is what happens next. If summer is strong enough, much of that ice melts away. If summer is weak, some of the snow survives. The next winter adds more. Year after year, a small leftover can become the beginning of an ice sheet. Ice also changes the planet by reflecting sunlight. Dark soil, ocean, and forest absorb energy and warm up. Bright ice reflects much of that energy back into space. More ice makes the surface colder. A colder surface preserves more ice. This feedback can turn a small orbital change into a much larger climate response. This is why the northern hemisphere matters so much. Around the Arctic, there is a great deal of land where ice sheets can spread. In the southern hemisphere, more of the high latitudes are ocean, and water resists rapid temperature change. The geography of Earth makes northern summer a climate trigger. Milankovitch understood that this trigger is controlled by three slow cycles in Earth's motion. They do not create winter and summer by themselves. Instead, they tune the strength of the seasons over very long timescales. The first cycle is obliquity, the tilt of Earth's axis. Today the axis is tilted by about 23.5 degrees. But that tilt slowly shifts over a cycle of roughly 41,000 years. When the tilt is larger, summers near the poles receive more sunlight and winters receive less. When the tilt is smaller, polar summers are weaker. A stronger northern summer melts more ice. A weaker northern summer lets more snow survive. Over thousands of years, that difference can decide whether ice retreats or advances. Earth's tilt is unusually stable because the moon helps steady the planet. Without that stabilizing influence, the tilt could wander much more dramatically, as it does on Mars. Our climate still changes, but Earth's axis does not tumble wildly. The second cycle is eccentricity, the changing shape of Earth's orbit. Earth's path around the Sun is not a perfect circle. It is a slightly stretched ellipse, and over about 100,000 years that ellipse becomes a little more circular or a little more oval. In real scale, the difference is subtle. Diagrams often exaggerate it so we can see what is happening. But even subtle changes matter, because Earth receives more sunlight when it is closer to the Sun and less when it is farther away. Right now Earth is closest to the Sun in January and farthest away in July. That means the distance effect slightly softens northern seasons. Northern winter happens when Earth is closer, and northern summer happens when Earth is farther away. But this arrangement does not stay fixed. The third cycle is precession, the slow wobble of Earth's axis, like a spinning top. Over time, precession changes which season lines up with the closest point to the Sun. About 13,000 years ago, the arrangement was closer to the opposite of today. Northern summer happened when Earth was nearer the Sun. That made northern summers more intense and helped melt more ice. When precession lines up differently, northern summers can become weaker, allowing ice to survive. The three cycles interact. Tilt changes the strength of polar seasons. Eccentricity changes how much the Earth-Sun distance matters. Precession changes which hemisphere gets summer near the closest point to the Sun together. They shift northern summer sunlight enough to help pace glacial and interglacial periods. The effect is not instant. Ice sheets are enormous. Oceans store heat. Carbon dioxide, dust, vegetation, and ocean circulation all respond and feed back into the system. The climate is not a simple machine with one lever. But the orbital cycles provide a powerful rhythm beneath the noise. Scientists can see that rhythm in ice cores and ocean sediments. Bubbles trapped in ancient ice preserve samples of old air. Layers of snow record dust, temperature clues, and greenhouse gas changes. Deep-sea sediments preserve chemical traces of ice volume and ocean temperature. When those records are compared with orbital calculations, the pattern becomes clear: Earth's climate has repeatedly shifted with the timing of these astronomical cycles. Not perfectly, not mechanically, but strongly enough that the connection cannot be ignored. This also explains something important about today's climate. Milankovitch cycles operate over tens of thousands to hundreds of thousands of years. They are slow. The rapid warming measured in the modern industrial era is far too fast to be explained by these cycles alone. Orbital cycles help explain why ice ages come and go over deep time. They do not erase the role of greenhouse gases, oceans, clouds, volcanic activity, or human emissions. Climate is layered, and each layer acts on a different timescale. The beauty of the Milankovitch cycles is that they connect the sky to the ice beneath our feet. Tiny changes in the geometry between Earth and Sun can alter summer melting, reshape ice sheets, change sea level, and influence the path of climate history. An ice age is not just cold weather stretched out over time. It is astronomy written into ice. It is the slow wobble of a planet, the shape of an orbit, the angle of sunlight, and the reflective power of snow all working together across thousands of generations. So when we ask how ice ages happen, the answer begins far above the clouds. Earth is not a passive ball drifting through space. It is a moving, tilting, wobbling world, and its long dance around the sun helps decide when ice grows, when it melts, and how the climate of an entire planet changes.